Hello and welcome back. In today's video we'll do a short run through all of statistics. Of course that's far too short to really properly review statistics, but we hope to cover most of the topics that you should at least have heard about. So what do we do with statistics? Statistics can be roughly divided in two groups. Of course there are many subtleties, but we can divide statistics in the field of descriptive statistics and inferential statistics. So descriptive statistics describes observed data. For example, we can use the mean, the variance and other metrics. We can make visualizations and also related is explorative data analysis, where we try to understand more about the data. Inferential statistics, on the other hand, is meant to draw conclusions from data or estimate properties. So for example, these are topics around parameter estimation, uncertainty evaluation or classification or hypothesis test, regression and so on. There are many classical methods in inferential statistics. We can also do probabilistic modeling and more recently machine learning. There are two schools in statistics that we briefly touch upon. These are the frequentist and the Bayes approach. So let's start with the descriptive statistics. We want to characterize a set of numbers which we call the sample. For example, this could be our measurements. One of the most frequently used metrics is the sample mean. Or we can also describe our sample by the sample median, where the median is defined by 50% of the data points are greater than this number and 50% are smaller. We can also define the sample variance. Here on the right hand side we can see an illustration of a few data points scattered about, and we can see that the mean and the median are not necessarily the same. What does that mean then? The mean and the median are not the same. In particular, when we add now outliers, we see that they behave differently. So we start with our original data set here on the left, and then we add one outlier to the right, indicated by the red circle. And we can see that on the top here we have the original mean and the original median, and they're fairly close together. And now that we have added the outlier, we can see that the median doesn't shift so much, but the mean does. So the mean is very sensitive to the, shall we say, the variance or the width of our data set. The more outliers we have, the more unstable the mean becomes. So this is where we need to be very careful in how we describe our data set. However, these simple metrics are often insufficient, and a nice illustration is Anscombe's quartet. These are 4 sets of data points, and they all have the same exact descriptive statistics, so they have the same mean, the same variance, and the same correlation coefficient. And you can see the 4 illustrated here. So 1 is scattered about, 2 is like a parabola, 3 is a straight line but with an outlier, and 4 is also a straight line with an outlier but in a different way. And if you look at the mean and the variance in particular from all of these data, you can see that they're all exactly the same. So using the mean and the variance is a good way to briefly characterize our data set, but it's not sufficient to actually describe it. Visualizations can help us to make more sense of the data. We've already seen now the scatter plot with the Anscombe's quartet in the previous one. And we can extend this, and by adding, for example, color and the size of the bullet points. Here on the left we see an example of such a scatter plot. It's called a bubble plot because you can also then modify the points, right? So we have more than one information in addition to the axis. So the axis, for example, is the bill spent on meals, and the y-axis is, for example, the tip given by the restaurant patrons, and then we can add colors or the size of the data points to indicate 1 or 2 more dimensions. Of course, the more dimensions we add, the more difficult this plot becomes to interpret. On the right hand side we have a bar chart. This can also give useful insights. And if we deal with data points, we need to have a firm understanding of what we mean by our sample, for example, of measurements, and what we mean to describe with this. In particular, we are often not so much interested in the sample itself, but we want to make descriptions of the wider effect, shall we say. And this is called the population in statistics. It's the entire group that we're interested in. So for example, if we focus on a sample of, say, 10 people, we can describe this with our descriptive statistics. This is the subset of the population. But we want to really make a description of our population. So that means that our sample must be representative of the population if you want to draw any conclusions, right? There are a number of pitfalls if we want to do this, and we want to briefly discuss a few. There's one nice example, and this is about cancer rates in rural counties in the United States of America. So here in this paper, they discuss this one, and they say the counties with the lowest 10% of age-standard death rates from cancer are scattered like this. And if we look at the distribution of where these counties are, we would say this makes intuitive sense. They're mostly in rural areas, and we could say, well, in rural areas we have a lot less pollution that might lead to less cancer. And people may generally lead a healthier lifestyle and so on. So we can reason our way why, for example, rural counties may have a lower cancer rate than more densely populated areas. Now, if we look at the highest 10% of age-standardized death rates from cancer, we can see that they're also in rural areas. Now, we've just reasoned our way that in rural areas, because of the healthy lifestyle, for example, or less pollutants, that makes sense that we have less cancer death rates. Now we say, if we look at the highest 10%, they're also rural areas. Of course, we could reason our way out of this again and can say, well, in rural areas, you don't have really access to good health care, so you would have a high death rate. So you don't have many hospitals, and in those hospitals, you don't tend to have high-class university hospitals and top researchers in cancer. So the access to excellent healthcare is more limited in rural areas than it might be in metropolitan areas. And of course, these are valid reasons which we could intuitively understand, but we are now left with the fact that the lowest and the highest 10% of death rates from cancer are in rural areas, and we want to reconcile this understanding. Now, what's really happening there is that rural areas have a low population. So we have small samples, which means in turn we have large populations. So there is no profound insight into town and country or metropolitan and rural areas. It's just that we've been tricked in the way we think about data. And this is really one of the key aspects that we always need to think about, because data can be represented in a very misleading way, or we can draw the wrong conclusions if we're not very careful in the way on how we analyze our data. And if you go back to the previous example of the lowest and the highest 10% of the death rate, each of the explanations make intuitive sense. And this is one of the great pitfalls in dealing in particular with small data samples. Now, in this video recording, we can't really do an experiment, but think about it on your own. Take 2 water bottles and measure the distance. And now try to come up with all the ways this could be wrong or misleading or ambiguous. Right? Take some time, pause the playback at this point and try to do this experiment in the comfort of your home and see what you can come up with. Now that you've done this experiment, this naturally leads us to uncertainties. Right? We always want to be able to quantify how accurate our result is. Remember that we don't measure the true value. In the example of the 2 bottles, we don't measure the true distance. We always use a measurement tool. So we have 2 types of uncertainties. There are statistical uncertainties, and there are essentially an effect of a limited number of measurements. Like this leads to a limited precision, and we can alleviate that by doing more experiments. So we have a larger sample leading to fewer fluctuations. But we also have a number of systematic uncertainties, for example, due to our instrumentation, our experimental setup, devices and tools that we use. And they cannot be reduced with more measurements because they're inherent in our experimental setup. If we find that our systematic uncertainties are very large, we need to think about how we can change our experimental setup. Or rather, before we start designing an experiment, we need to be clear of how many measurement points we're going to take. So what is our anticipated statistical uncertainty? We need to balance that against the systematic uncertainties. It also doesn't make much sense to reduce the systematic uncertainties by buying extremely expensive equipment if we're limited by the number of measurements. But the two need to be balanced, right? So we don't want to be dominated by systematic uncertainties. A key issue in statistics is predictability. So what do we mean by that? We could either have systems that are fully calculable, for example using differential equations like the harmonic oscillator that you see below, or we could have systems that allow no prediction whatsoever, like for example lottery numbers. Like if you could predict lottery numbers, there would be no point in doing all of that. Now these are sort of the two extremes, and often it works in simplified situations. For example, we can always describe a simplified version of our setup. In physics, we often make the joke of a spherical core in a vacuum, and then we use methods from statistical inference to solve all of this. But in reality, these two extremes are most of the systems are between those two extremes. So we have a statistical behavior in the sense that it can be modeled by a distribution and it can be predicted up to a given point, but not exactly. So we need to describe everything in terms of probabilities. So what do we mean by that? We have a very popular understanding in our everyday understanding of what probabilities mean, and there's a nice illustration of, for example, like the weather forecast, probability between 0 and 100% or 0 and 1, like not gonna rain, rain, gonna rain. And you can see that if we follow different aspects of our everyday life, these interpretation of probabilities shift between, for example, the local news presentation, investment banker, weather forecast, political journalist, and so on. Actually, the CIA made a detailed study of this, and you have here the resulting graph on the right. So they asked people what they mean by the statement almost certainly and give it an assigned probability of an event happening between 0 and 100%. And you can see that there's quite some scatter if you ask a lot of people what almost certainly means. It's anything between 80 and 100%. Chances are very slight, it's anywhere between 10 and 0 and 10% for most, but you have at least one in the high 40s as well. So that means that our intuitive understanding of probabilities isn't quite so intuitive after all. Now let's discuss what probabilities are. Let's start with the simple example of a coin flip and discuss the frequentist approach. There we have a very intuitive definition. So you flip the coin over and over and over again, and then you count the numbers you have, head versus tail. And then we can say that as we have a large number of coin flops, the probability of observing a head is the number of heads we observe divided by the very large number of coin flips that we have. Of course, we can extend this to multiple outcomes, like for example, take a dice. There we have 6 different outcomes, and we repeat throwing a dice, and for a fair dice, we expect that each number comes up 1/6 of the time. Here, we need to introduce the key concept of a random variable. So, our random experiment is that the experiment for which we cannot predict the outcome with certainty. Like our coin toss. We cannot say for the next coin toss if we have a head or a tail each time. We don't know which, but we know it's one of those two. So these are the outcomes, head or tail, and our sample space is the set of all possible outcomes, head and tail. So the assumption in our frequentist approach, like in the coin flip, is that we can repeat our experiments, and so we can define this probability. This is quite different to what we mean by an analytical variable. For example, the analytical variable is a solution to analytical equations, differential equations, and so on, a specific value a solution. For example, differential equations plus boundary conditions, and so on. The random variable, however, maps an outcome to a number, for example, obtaining head when flipping a coin. So we want to express this numerically and in terms of probabilities, and we don't know the result of the coin flip a priori, and it can be different each time. So we want to assign a probability measure that assigns probabilities to events, and events have 0 or more outcomes. Bit more formal still, this is defined by the Kolmogorov axioms. So these are the formal definitions from Kolmogorov from the 1930s. So we consider our single events, even that exclude each other. So we have our sample space S, it's a union of all events, and then we have elementary events, for example, head or tail, and then we have the probability for such an elementary event. And then the following axioms hold: the probability is always greater or equal to 0, because you cannot have negative probabilities. The additive and they crucially need to be normalized. Something needs to happen. If you flip a coin, you can have either head or tail, but you cannot have no head nor tail or anything in between. You need to end up with head or tail. So let's have a quick probability cheat sheet, and of course there's much more to it and a lot more definitions and things to remember, but this should guide you through it. So remember, all probabilities are normalized to 1. Probabilities are always between 0 and 1. In the frequentist approach, a probability is like what we observe by the number of our sample space, like the number of our coin flips versus all the flips that we've done. The complement is 1 minus the probability. This is in the upper left corner in the right box. So these are the core things that you need to keep in mind. Things that you also need to remember is the conditional probability. When we say it A given B, so the probability A given B is essentially the what happens, do we observe A if B has already happened. So if, for example, B has happened, what is then the probability to observe A? For independent events, A and B just are the multiplications, so we don't have any entanglement, shall we say, between those two. For dependent events, these are depending on the conditional probability. Independent events, for example, imagine dices or coin tosses. If you flip a coin and again, right? So one event doesn't influence the next. For dependent events, this is different. This is why I put the card there. Take a deck of playing cards, for example. So it's not, if you draw a card, they're no longer independent, right? If you don't put the card back. If you take a card out, the probability changes for all the other cards to be drawn because you've removed some from your sample space. It's also important to remember joint and disjoint probabilities is essentially the overlap between them. When we deal with probabilities, now that we've covered the random variables and what probabilities are, we need to describe a few very important probability distributions that these random variables describe. The simplest one we've already discussed, it's called the Bernoulli trial. It's a single experiment with a binary outcome, success and failure, or head or tail, like our single coin toss. Now, if we repeat such a Bernoulli trial n times and observe k successes, this leads us to the binomial distribution. So for example, instead of saying what is the next coin toss, we want to say, if we toss the coin 10 times, what is the probability of observing 5 heads? And you can see the distribution here on the right, and of course 5 has the highest one because we have a fair coin and it's equally likely to have head or tail, but it's perfectly possible to observe only 1 or 2 heads. It's just not very likely. The negative binomial distribution is sort of its complement. You have n trials and k successes for the binomial distribution. Now, alternatively, we say how many failures do we observe before a fixed number of successes, right? So these are related, but the question we ask is subtly different. For example, for a fair coin, how many tosses do we need to do before we have 5 successes? The Gauss or the normal distribution is one of the most important distribution overall. It's a continuous distribution defined between minus infinity and infinity, and it's so important because of the central limit theory that then states essentially and very briefly the sum of n independent random variables will converge to a Gaussian distribution. So if you have many contributing factors, you always observe a Gaussian distribution, and this is what you frequently find in nature in your experiments, and it becomes important for quantifying your uncertainties because almost always you make the assumptions that your uncertainties are due to so many factors that you can assume they're Gaussianly distributed. Of course, that's not always the case, but in most experiments and also simulations we make this assumption. We have then also the exponential and Poisson distribution. There are different aspects of a random systems where we only know the mean number of events per unit time. So the Poisson distribution describes the count data. That means like how many events do we observe per unit time given that we know the mean number. Say for example, and this is what's shown here on the top right, we know that per unit time we have a mean of 15 events occurring. So if we look at 1 unit of time, what's the probability of, say, observe 5, 10 or 25 events? The exponential is like the cousin to it, and it describes essentially how long we have to wait until the next event happens. And what you can see is the next event, the highest probability for the next event is now. A key distribution in many systems is the Weibull distribution. That is described. This describes the failure of material under stress, or components or machines between failures and reliability engineering and so on. The formula is given here on the top right, and you can see from the graph that it has very distinct behavior depending on the parameter values. So for k is smaller than 1, the probability decreases with time. That means, for example, faulty components will fail early and are weeded out. If k equals 1, that means that the probability is constant, and then the Weibull distribution becomes the exponential. Or k is smaller than 1, that means the probability increases with time, for example, material fatigue. And this distribution is essentially what drives all the concepts of predictive maintenance. Of course, that was a very, very short overview of distributions, and you can see that there are so many distributions and they are related in multiple ways. So the obvious challenge is, how do you know which one to use? And this is why you need to be intimately familiar with the system you want to study with statistics, so that you are familiar with which distribution is most appropriate for your use case. Now that we have a distribution, we want to characterize it. How do we do this? So a distribution is the probability is always defined on an interval, right? It's not a point of this distribution. You always have f of x as our probability distribution, and you always give a probability of an event occurring between 2 points. The key one is the expectation value, e of g of x, right? And this is the convolution of our function g with a probability distribution f. The mean is a very special case, and because it's so frequently used, it has its own symbol there, and you can see it's over a continuous distribution. We have the function g is x times f of x, and the convolution of that is the mean. The variance is defined of the expectation value of x minus the mean in bracket squared. And you can see on the right hand side how these different values are. You can have, of course, the mode, that's the highest point. You can have the mean, that's the expectation value, and as we've defined on the sample, you can have the median, and that is the point where 50% of the distribution are greater than this point and 50% are smaller. And as you've seen, the mean, the median, and so on, they don't necessarily need to be the same. They are for a symmetric distribution like the Gauss distribution, but they are in general different because the distributions are typically skewed. Now let's discuss hypothesis testing. Hypothesis testing is essentially a statement where we want to use data to verify and falsify. For example, is the coin unbiased? Is algorithm A better than algorithm B? Is this a dog? Does the medicine work? Is the accused guilty? And so on. We have two concepts we call H0, the null hypothesis. That is the status quo, the medicine doesn't work, nothing effect, no effect, nothing happens, and so on. And we have H1, the alternative hypothesis. This is the alternative to H1. So, for example, the medicine does work. So we want to establish with a degree of confidence if we can reject the null hypothesis, and that means we accept the alternative hypothesis. In a simple case for medicine, we could say we want to make sure that this medicine actually works. One example is the fair coin. So, is the coin fair? The null hypothesis is that the coin is fair, and the alternative hypothesis is that it's not fair, so that the probability of heads, for example, is not 50%. So we now do 100 coin tosses and we observe 63 heads. Is that okay? So how do we do that? With statistics. So we do look at the binomial distribution, as we've said earlier, because we have repeated Bernoulli trials. And because of the central limit theorem, we have many independent contributions. We can approximate the binomial distribution with a Gaussian. You can see with the overlay on the right that this works quite well. The assumption is quite well justified, so let's go with that. We need to now define a test, statistics, and this is called a Z-score. So for a fair coin, P equal head means 50%. We expect that about 50% of heads in 100 toys are observed. Now we observe 63, is that okay? So we define our test statistics. So we have the expectation value versus the population mean, the population variance, and the number of events. So remember, we approximate this with Gaussian. So we want to make sure and calculate how far away is our result from the expectation. What does this mean? Here we observe from our sample 63 heads over 100 tosses. Right? We know from the population, this is our assumption, we would observe 50, and then we have the population variance. So we put this in. This is the variance of the binomial distribution which goes in, so sigma squared is NP 1 minus P, and here the Z-score is 2.6. Right. 2.6. Is that good? So we look again at our Gaussian distribution. This is why we made the assumptions. Look where 2.6 is on the left-hand side and on the right-hand side. And we can see that this Gaussian distribution is very small at this value, but not 0. So should we reject the null hypothesis? And we typically have a threshold. It's called the p-value. That means 0.05. Here, if we calculate this p-value, and this is essentially the area outside, the p-value is very, very small, and so the coin is very likely biased. We shouldn't observe 63 heads in our fair coin. What is this p-value? It's very often used, but it's not an easiest concept to grasp. Let's go with the informal definition in quotation marks that comes from the American Statistical Society. It says informally, a p-value is the probability under a specified statistical model that a statistical summary of the data, like the sample mean difference between two compared groups, would be equal or more extreme than its observed values. This is not very clear, is it? Now, more colloquially, for a test statistic t, the p-value is the smallest value of alpha, so the p-value, for which the observed data suggests that the null hypothesis is rejected. In the setting, the smaller the p-value, the more unlikely it is that the data comes from the distribution specified by the null hypothesis. So essentially, the p-value is a number that defines how likely it is that this observed effect is true to the null hypothesis, or if we should reject the null hypothesis. So that we typically say, if we calculate the p-value, we say it's smaller than 0.05%, and this is the commonly used threshold in many but not all sciences. It implies that 1 in 20 discoveries we do with this threshold are wrong. The p-value measures are essentially a measure how incompatible the data are with the given hypothesis. This is what we mean by reject the null. It doesn't imply that the alternative hypothesis is true, it just means that we reject the null hypothesis. And a non-significant result does not mean that the effect is not there, it's just that we cannot, with the given size of the data, measure this. It also, the p-value does not relate to the effect size. We may reject the null hypothesis with high significance, but the size of the effect is far too small to be of importance. So for example, we could say a new drug for heart disease, this could be very significantly improving patients' outcome, but the outcome or the improvement is so small that whether you give the drug or not doesn't really make a difference in everyday life. You can measure this in a clinical setting, but for the patients itself, it may not be enough. So how do we do this? We, for example, can use the test statistic, the t-test. In particular, we've done this before. We use the z-score, right? And we saw that we have the population mean, the population variance. And if we know this, for example, in our fair coin test, we said if we know this, we could do this, because for a fair coin we make this assumption and we know what the population of all fair coin tosses are, like the 50%. Right? And we can then use the approximation of the Gaussian and see how far our result is from the expectation. In general, we don't do this. For example, we need to replace this with a sample variance, and that leads us to the t-statistics, as you can see down there. And then the distribution is no longer a Gaussian distribution, but follows the student t distribution. The same concept and the same approach follows to calculate the p-value essentially, but we need to make different assumptions of what we know about our sample and our population. So far we just look at the null hypothesis assuming a Gaussian. More realistically, we have two distributions, like one distribution for our hypothesis, null hypothesis to be true, and one distribution for our alternative hypothesis to be true, right? And how do we decide between the null and alternative hypothesis, and how do we get the statistics? Of course, in the best of all cases, these distributions will be very narrow and far apart, but of course, in most realistic distributions, this will not be the case. So as you can see here, they tend to overlap. And that means that if we are in this overlap region, we will make some mistakes. Like we will accept the alternative hypothesis even if the null hypothesis is true, and vice versa. So we need to define a cutoff point where we can say this is the point where we accept the alternative hypothesis and reject the null hypothesis. The simplest one is, of course, to take the critical value in between, as we've said, but this may not be enough depending on what you want to be penalized for in the errors. Essentially, this is also what lies behind the classification as we do in machine learning. You predict a probability outcome for the one class and for the other class, and then you need to make a choice which class to assign. So you have two kinds of errors, the errors of first and second kind, because these distributions overlap. So the error of the first kind, or type 1 false positive, this means that the null hypothesis is true, H0 is true, but the value is beyond the cutoff on the right. So we accept H1 although it's wrong. The error of the second kind, also type 2 error or false negative, is the opposite. The alternative distribution is true, but the value is now in the other way round. So we accept H0 although it's wrong. So we can visualize this in this little table there. We want to be on the diagonal, but depending on how wide the distributions are and where our cutoff point is, we either make a type 1 error, alpha, or a type 2 error, beta. Now it depends on your application which one you would actually favor. So it depends on the setting. You can take this little joke and say you have a doctor and looking at a very sizable man and say, oh, you're pregnant. Obviously that's not true. Or you look at a pregnant woman and say you're not pregnant. So these are your type 1 and type 2, your alpha and beta errors. So which one is worse, and that you need to decide case by case. So which value do you take? There's no simple answer. It really depends on, in the given application scenario or analysis scenario, what does hurt you more, a false positive or a false negative? How pure do you need H0 and H1 to be? And you also need to consider what's the base rate of 2, right? Are these two more or less equal outcomes, or is, for example, H0 much more frequently in your data than H1 and so on? So it depends a lot on what you actually want to analyze and the implications for the downstream decision making is where you place your cutoff value. Let's do a little example. So let's ask a student 12 true and false questions, and you have correct and error answers, and you have the following sequence. Do you want to, now you want to establish if the student guesses the answer but doesn't know. That's our null hypothesis. How do we want to do this? Think about which assumptions you make and how do you want to model this. So you could do this with approach 1. 12 Bernoulli trials. Guessing means 0.5% probability for the correct answer. Because we have independent events, we go back to the binomial distribution. So the probability of observe 9 successes out of 12 trials, and the p-value is 0.054. The probability is 0.054. The corresponding p-value is 0.73. It's greater than our typical threshold of 0.05. So this is compatible with the null hypothesis. The student likely just guesses. However, we could also say we keep asking questions until the student gets 3 wrong answers. And here in this example, it took 12 questions to do this. Now, we don't model this with the binomial distributions, we do this with the negative binomial distributions, right? So here the corresponding p-value is 0.033, which is smaller than 0.05, so the student is unlikely to guess. We reject the null hypothesis. Now, for the same data, correct, error, correct, error, enter error, we have now 2 answers. The student guesses, approach 1 with the binomial distribution, we fail to reject the null. Or the student does not guess, approach 1 with a negative binomial distribution, we reject the null hypothesis. Both solutions are statistically valid, and it drives home a point. The data do not tell you everything. And this is one key thing that you also need to remember when you read and also write paper. Just writing the data without clearly outlining how the experiment is done and how you make a retrieval does not work. Because if you leave out the crucial information, how you design your experiment, in our case, do we have 12 predefined questions or do we keep on asking until 3 are wrong, you can come to very different conclusions. The next topic we briefly touch upon is regression. Essentially, we map a set of data points to a value. So we have measured a number of points, x1 to xn, and map this to our predictor. Or it's a function, right? We have x, y hat, this is our predicted value, is some sort of function of our input depending on some parameters. Essentially, f describes the relation between our measured values and the predicted value. Here it's important to know that all variables, x and y, are random variables and that describe probability distributions, and the typical simplification that we do is the expectation value of y given x is this function. So we predict just one value, the expectation value. And this is what you, for example, do in simple linear regression. You have a very simple model that you take your data in and out comes a single number, and most regression models follow the same approach even if they're more complex as such. So how do you choose the functional dependency? Right, the simplest, as we just said, is the linear combination of all features. So you have for some variables, you give them a coefficient and have a linear combination of them. Essentially, this is a straight line point across all features, and depending on your data, this may or may not work well. And you do this by minimizing the residuals between the observed value in your training data and the predicted value. The advantage of this is very simple, both conceptually and also computationally. It's quite interpretable because you have the coefficients that are directly related to the relative importance, and it's always a good baseline to do this because any more complex model that you have should be able to beat it, otherwise you wouldn't need it. The disadvantage is that you don't incorporate any correlations between the variables. If you go back to the definition of linear regression, you see that all variables are treated as independent, which is of course not true in almost all realistic cases. You also don't have nonlinear relationships between variables. It's quite unstable with respect to outliers and doesn't take all the information into account that we have. We can extend this, of course, to allow nonlinear relationships, for example, have a polynomial degree. Then we need to decide how many terms we have. If we have too few, we don't have enough flexibility. If we have too many, and then we don't capture the essence of the data and just fit the noise. Right? So for example here, if we have just a straight line for this data set, it's obviously not enough. And if we have too much degree of freedom on the right hand side, we have all the wiggles that are unlikely to come, especially like between this kink up there between the first and the second data point is unlikely to happen. So what can we do? The key idea here is regularization. Like we allow a flexible model with many parameters, but penalize using this flexibility. So instead of just minimizing the test data, the training data Y with the prediction model or regression model, we add a penalty term with a given strength lambda. That's a free parameter that we need to tune, and some sort of penalty that depends on some parameters. There are two main ones that are often used: the lasso regularization, where we take the absolute values of the coefficients in the linear regression, and the ridge regression, where we have a quadratic penalty. You can also do a combination. This is then called elastic regularization, where you have both lasso and ridge. And if you do that, you can see that both models make this a lot smoother. So you go from the very wiggly line to the much smoother line, and you can see on the regression coefficient that the ridge regression still has a very large variability of the coefficient, and the lasso regression really tries to minimize the coefficients as much as possible. And you can see that in this example, this may be a little bit too much. It depends on what you want to do in your use case and how strong you want to use this regularization. How do you choose the functional dependencies, right? So we just used the simple linear regression or the extension with polynomials. There are many more options that you can have. For example, you can build a specific probabilistic model if you have a lot of knowledge about your use case. This is one way to go forward. You can use generalized additive models, or you can use now machine learning. So key takeaways for our brief reminder of statistics, right? We can use statistics to describe and characterize data. This is descriptive statistics, but be careful. The summary measures are often insufficient. We can make predictions or inference using statistical model. This is called inferential statistics. The key concept you should keep in mind is the random variable that maps outcomes to numerical values. These are our probabilities that we always talk about. And random variables follow a specific probability distribution, or often a mix of distribution. Context matters. Remember our experiment discussion about the student and the 12 questions. The data do not tell everything. We need to understand the process that generates the data. We need to understand the context to make the right choices and about how we evaluate the data. A key aspect about statistics versus machine learning: in statistics, we build an explicit model using our expert knowledge and tune the parameter using the observed data. In machine learning, on the other hand, we learn the model from the data, including the parameters.